The first topic is what is the signal? In this lecture, we need to understand what is the signal and what is systems, how to express the signal and the system. To describe that one, we need to understand the framework. Framework means the terminologies to describe signal and system. Here shows some terminologies. The CT means continuous time, DT means discrete time. So continuous time or discrete time signals. There's two different domains that exist. One is continuous time, the other one is discrete time. And transform. Transform means from one domain to the other domain. So we need to change the domain. That is transform. And there is some special function, exponential function, sine function, impulse, like that kind of things. To testing the system, we are using those kind of the testing signals. And also system described based on the continuous time or discrete time. Like that kind of thing is a key terminology to understand the signal and system. Let's start. The first one is to know the continuous time or discrete time signals. We know that what is the function. Function is a mapping from domain to the range. Okay, here is some domains are here. Let's the domain variable is t, and function map the domain to the range. In this case, range is v. We are mapping from domain to the range with a function. So function is mapping from domain to the range. When we handle the signal, usually domain is a time or space. A range usually the voltage or current signals. Okay, so at this moment you need to know what is the domain and what is the range. Usually domain is an independent variable. Here shows that the typical signal patterns are shown here, figure 1.1. So time is a domain. At a given time, the signal is given like that way. This one is a range. This one is domain. So we need to know that what is the domain, what is the range. When we taking transform, we change the domain. Usually we are changing the domain. Okay. Then we define what is the function, and signal can be defined like this way: a function of time or space, because the domain is time or space. It's a function of time or space containing informations. So what is the informations? To look at the information, the terms, let's see this one. Pattern of variation over time. It means that the sound or vision changing over time. Sound is the fluctuation of sound pressure or vision light intensity. Like that kind of fluctuation are detected by sensors. Sensor converting those variation into electrical signals. So signal, in fact, a electrical change or variations that contain information. That's another viewpoint of signals. So we look at the signal in several different kind of views. The first mathematical viewpoint is a function of time or space containing information. That's the mathematical viewpoint. But physical viewpoint, it is an electrical variation due to the sound, vision, or pressure, like that kind of physical environment change are converted into the electric signal through the sensor. Let's see here that we have ears or eyes. Ear detecting the sound pressure, and in our sense it's a microphone. Microphone pick up the sound pressure change and converting that one into a electrical signals. The light intensity also detected by the image sensor, like a camera. So by detecting the light intensity, that is converted into electric signal. That's the signals. So I introduced some concept about signals. To get some more physical idea, I would like to show you that how to create the signal and how to make it, how to handle that one. I would like to show you. Here shows a simple example. Here is a sine wave the amplitude is 1, the frequency tone is 440, the sine wave 440 Hertz. Simulate over 5 seconds. During the 5 seconds, it's simulated and stored at the output sine dot wave functions. Taking simulations, it shows that some sinusoidal wave like this one. So amplitude is 1, the sinusoidal signal shown here. That is how to generating the sound wave here. You can hear the sound output wave. Okay, here. If you play this one, you can hear the sound. Okay, this is singleton sound generated here. Okay, we created the signals. How to visualize that one? To do that, I would like to suggest this one. So this file is sound file. We read out that one and make it plot like this way. So the first plot is just the signal is changing over time. So domain is time. The range is voltage level. Okay, so we can plot the signal over time. So the next plot, I just briefly explained that one. So let's learn this one. Read the signal and make it plot. Here shows that the result. I said that the signal is plotted over time. Okay, the x-axis is time. So you can see a sinusoidal signals are plotted over here. But bottom plot, the domain is not the time. The domain is frequency. So the time domain is converted to the frequency domain. In the frequency domain, the same signal can be expressed as just a single point. The amplitude is 1, but the frequency is 440. So this is 1000, so the frequency is 440. So we can convert the time domain signal to the frequency domain. We can convert that one by some special transformations. At this moment, you don't need to know the detail, but signal can be expressed over time like this way, but that can be transformed. Then it's quite simple, very simple signals, okay, in the frequency domain. So I show you that how to plot the signals and what is the signal. Okay, show you that the audio signals, but there is another important one is image signals. Image signal domain is space. Okay, so to show you that I read out the image signals from here. So that is read out from these files and plotted that one over here. The image is plotted up here and the image value also plotted in here. So this is the image. Left side plot is this image plot, and the right hand side just plotted the same figure. The light intensity is plotted over the domain. In this case, the domain is a space. Okay, it means that the image changing from width from 0 to the 512 and height 0 to the 512. Size of the width and length is 512, 512. So the width changing from 0 to, in this direction, this is x-axis, 0 to the 512, and vertical one changing from 0 to the 512, this is y-axis. So if you align the curve like that, you can a little bit similar patterns are shown here, but this one is just a 3D curve. So light intensity are plotted over the domains. Okay, so sometimes some point like this point is very high intensity, but the dark side is a low intensity. So that is plotted over here. So signal can be plotted over time or over space. Show you two different signals of one is audio, the other one is image signals. I show you. And then lastly, I show you another the audio signals. This one, okay, let me show you first. Okay, by running, it plot the two different time domain signals and two different frequency domain signals. Okay, the upper one is a time domain signal. This one is a left side audio, and the right hand side audio is here. At this moment, it's capturing my voice. If I speak out, then the sound pressure levels are represented here. So up and down, those signals are the sound pressure level. That signal converted into frequency domain. You can see the x-axis now. This one is bottom two is showed at the spectrum, so that the domain is frequency. So spectral contents are shown here. So signal can be expressed in in such a way. If I generate a single tone, how will it look like? Here shows a very strong single tones are generated like this way. So signal can be expressed in this way, that usually we are plotting the audio over time. So this is a time domain, that's the domain. This one is a range. Range is the electrical level. The electrical level is directly proportional to the sound pressure, how loudly I speak out. That is the information for that one. Okay, so I think that you get some idea what is a signal at this moment. Okay, signal can be classified in two different groups. One is a continuous signal, the other one is a discrete signal. And the continuous time signal is the signal is defined all the time. At any given time, signal is defined. Okay, that's a continuous time signal. But the discrete time signal is defined only specific times. So, and the sample time, the signal is defined like this way. The dotted one shows that the sampled signals. In discrete time signal, is only defined in specific times. In between sample, it means that in between these samples, signal is not defined. It is undefined regions. So discrete one is defined only specific time point. So to express that one, usually in the continuous signal, we are using the time variable. So, but the discrete one, we are using the index, the sequence. But you know that the sequence also related to time. In fact, the time difference between sample is specified. So even though we are using index number, there is a time is related to that index. Okay. And also the continuous and the discrete time has domain variable like this one. Both of them is time, but the one is the time, physical time. The other one is a index sequence. Okay. How strong the signals to express the one? Look at here. That we can see this one is related to the voltage fluctuation over time. If a stronger signal, then the amplitude will the higher. But the smaller one, smaller amplitude are shown here. But usually in electrical systems, if we multiply voltage to the time, then the dimension becomes the power, watt, joule per sec. That's the power dimension. So voltage times current becomes the power. How strong the signal, we can express that one into a power, how large it is. By use of Ohm's law, we can convert this the current becomes the voltage divided by resistance. So by taking the square of the signal, it's proportional to the power. So this is power signals. To get the another point of view for how strong the signal, we can integrate the power, then we can get the total energy. So to find out the amount of energy over time, between T1 and T2, by taking the integration during that period, then we can get the energy. It means that the power is a joule per sec. By multiplying time dimension, so the unit becomes joule. So we can get the amount of energy of the signal by taking integration the power. So we need to understand what is the power signal and what is the related total energy for the signals. So higher, the stronger signal will have higher power and higher energy. Then what is the average power? The average power is the average out for the given time. So by taking the integration over the time period and divide by the times, then the dimension becomes joule per sec. So the integrated energy divided by the time period, then it gives the average power over time. But you know that what's the difference between the power signal versus average power? Average power is representing the power is over time. So this is specific value. But power signal is a process. It's changing over time, fluctuating. But this is not changing. It's not fluctuating. It's a specific value. Okay. So all this one is related to the how strong the signal. Okay. But when we handle the signal, we usually taking the resistance equals to 1 ohm. It doesn't matter that this resistance value. Make it 1, it's very simple. By just taking the absolute square, that gives the power is averaged, that's integrated over T1 to T2. By integrating the power, it becomes the energy signal. In continuous system, we're taking integration, but in the discrete time system, we're taking the sequence sum. The absolute taking square is very important. In some signals, the x value is complex number. In that case, we are taking the magnitude of the complex number and taking square. That becomes the amount of energy over time between the T1 and T2. And it's similar to discrete time energy. It's just taking the square, the absolute and the square. That gives the amount of energy of the signal. What about the interval is infinity case? Okay, here minus infinity to infinity. The summation is minus infinity to infinity. The integration is continuous domain. Summation is a discrete signals. If the absolute scale integrable, it means that this value is a finite value, then that is called finite energy signals. Okay, the integration is possible, or summation is possible in discrete time signal. That is called finite energy signals. If this value is finite, then the power, average power, becomes the 0. It means that here shows that the average power of the definitions, the whole energy integration, energy is given like this way and divided by the period of time. T goes to the infinity, then if the integration is finite, then obviously power goes to the 0. Average power goes to 0. That's the explained here. If finite energy signal is a 0 average power signal, it's the same for the discrete one. The other cases like this one, if finite average power signal, it means that if this value is finite, then energy should be infinity. It means that the denominator goes to the denominator goes to infinity, but the power should have finite value. The numerator also should be infinity. That's why if signal has a finite average power, the energy should be infinity. Or if energy has a finite value, then average power should be 0. That is explained here. And in sometimes both power and the signal are not finite. It means both of them infinity. One of the example is a ramp signal. Ramp signal is this one. Ramp signal xt equals to t. At t equal if greater than 0. So this is ramp signal. So ramp signal has the infinite power and the infinite energy signals. So this doesn't mean that if the energy is infinity, then power is finite. It doesn't be valid. So you need to classify signals. First, you have to check the power is finite or zero. If power is finite, then energy should be infinity. But if energy is finite, then power should be zero. Okay. I already explained how to plot the audio signals. In the time domain, audio can be plotted in this way: time versus the sound pressure level. Sound pressure level proportional to the electrical level set here. And the same signal can be expressed in the frequency domain like this simple value. Okay. The image signal also can be plotted with the image, and the image can be plotted over here. The right hand side, this figure shows that the light intensity changing along the law of this first one. First law changing from left to the right, that is plotted over here. So you can see that the first part is a little brighter. That means a little higher intensity. But right after that, there is some dark period existed here. That pixel is a low light intensity, and then there is a little higher, some small flat top, and some bright pixels exist here, and another dark period exists here. So the first law are plotted in these patterns. The second and third law also plotted. In the previous plot, I plotted all the law. That becomes the 3D image. In the bottom two, the plot shows that the differentiation of the image. By taking the differentiation, here shows a difference kernels. Look at here. This kernel looks like this one. 9 pixels. Okay, these 9 pixels has a weighting factor is -1 and -1, -1, -1, -1, -1, -1, -1. So 8 is -1, but center is 8. Then the difference between each pixels side by side, that value expressed at this value. So by these kernels, if you're taking the convolution, then we can differentiate the image. At this moment, I do not explain what is the convolution, but we will study that one in several weeks. Convolution, the concept of convolution, and also the how to implement the convolution will be studied later. So anyway, we can differentiate by this way, but the pixel distance is very near, then image is not that clear. But we can extend that kernel in that way. Then we can a little bit figure out the line trace of the image. So that is shown here.